I'm going to go through a couple of examples now with you on how to determine whether a function is even or odd. Okay, recall that we've defined even and odd functions, so that an even function is any function where f of negative x equals f of x. And remember, that comes from the idea that an even function has y-axis symmetry. If you have y-axis symmetry, then plugging in a positive or negative value for x will result in the same output, f of x. Okay, so a positive or negative input results in the exact same output. With origin symmetry, or an odd function, those two go together. And I always remember it, the O's go together, right? Origin symmetry and odd function. With an odd function, origin symmetry, if you input opposite signed x values, you will get out opposite signed y values. Okay, so that's how that comes about. So f of negative x is equal to negative f of x. Okay, so my first example here, I've got f of x is 3x to the fourth minus 1/2 x squared. Okay, so to determine whether it's even or odd, or it could be neither, if neither of these equations hold, then you have no symmetry at all, and so that's fine too. That could be an option. In this case, to determine whether or not I have even or odd symmetry, or neither, one of the simplest ways to do that is to plug in a negative x. Plugging in a negative x, because it occurs in both of these equations, is a short way to determine which type of function we're looking at, with only having to do this one time. We don't have to try to repeat the process for one versus the other. Okay, so I'm going to start off by plugging in a negative x into the function. Now, when I plug in negative x in for the x's, when I simplify the function, if I were to get the exact same thing as f of x, the original f of x, then I know I have an even function. If I simplify it and I get the exact opposite of f of x, it means an extra negative sign, then I know I have an odd function. And if I don't get either of those cases, I don't get the original function back, nor do I get its opposite, then I have neither forms of symmetry. Okay? So I plug in the negative x in place of the x. So I have 3 times negative x to the fourth minus 1/2 times negative x squared. Okay? That's just a substitution. Now, I'm going to simplify this. Remember that when you have a negative raised to an even power, that's always a positive number. Okay? In fact, anytime you have a negative raised to an even, that's going to be the same as just the number without the negative raised to that same power. Okay? So the sign won't matter, the answer will be the same. And so this, you could equate this to really the definition of exponents, because you're multiplying 4 negatives together. All right, so when I simplify this, negative x to the fourth is the same as just x to the fourth. And negative x squared, by the same reasoning, is just simply x squared. And that's just by the, I guess I would call that the definition of exponents. So I'd probably, if I was doing this as a 2-column problem, I'd probably throw in here definition number 2. Just saying that these are repeated multiplication, and when you have an even number of repetitions of a negative, you get a positive, right? Maybe I could have described that better, but I'm just trying to use the properties in my index here. Now this happens to be exactly the original function. Notice everything matches up perfectly. And so this is equal to f of x. Now if f of negative x eventually is equal to f of x, the original, then I know that I have this first condition, which is an even function. So I could say that this is an even function. Okay? There's my answer for that one. All right? So that's really all we're doing is trying to simplify the function when we put in negative x. You simplify it as best you can, and then just determine which type of function you have, whether it goes back to the original or whether you get the opposite of the original. Okay, let's try another example. Let's look at f of x equals, let's go with something like negative 2x cubed over, well, I don't know, x squared minus 5. Something like that. We'll see what happens here. Okay, so again, same idea. You plug in a negative, so you get negative x plugged in, and then we see what we get out. Okay, so I'm going to replace all the x's with a negative x. So we get negative 2 times negative x cubed all over negative x squared minus 5. Okay, now I think about my exponent rules again. When I take a negative and raise it to an odd power, that's 3 factors of a negative. Negative x times negative x times negative x. 3 of them make a negative. And so this is equivalent to actually having negative 2 times, negative 2 times negative 1, or negative 1 times x cubed. Okay, so essentially move the negative out, and that's again because it's a negative. A negative cubed is going to be negative, so you could think of that as a single negative 1 times the x cubed. Okay, now I'm writing that a little bit funny. I could write that without the parenthesis there or do something else, but I'm trying to separate that negative 1 factor, make it stand out a little bit. Then on the bottom here, remember, a negative squared is going to be positive. That's again the definition of an exponent. So I would write that as x squared minus 5. And again, the reason that's the definition of an exponent is because you're repeatedly multiplying a negative, and a double negative will be positive. Now, if I were to just take this negative 1 and move it out in front of the fraction, I could write this as negative, or negative 1 times the rest of the fraction, which is negative 2x cubed over x squared minus 5. Which seems like a weird way to write that. However, it's useful because I can now see that this fraction matches the original fraction. Okay? So what I'd like to do is try to figure out how to get the original fraction back in, or original function back into this new one. And I can do that just by pulling out this negative 1 factor. Well, in the end of the day, this is just a negative, this is the original f of x, so this is equal to negative f of x. Okay? And so if I have negative f of x as my result, I must be looking at an odd function. Okay? So I would say then that this original function is an odd function. Okay? All right. So the even odd idea again is really found simply by plugging in a negative x for all the x values and then evaluating or simplifying the function to see if you get either the original or its opposite, or maybe you get neither of those two options. Let me show you another example. You can probably guess where I'm going with this last one. Okay, here's an interesting one. X to the third plus the absolute value of x. Okay. Now x could be either positive or negative to begin with, so this kind of makes sense. But if I plug in a negative x, again I plug it in for each of the terms, each of the x's. Well, we know that an absolute value, well, actually, let's start here with the power. Negative x to the third, when you apply the power, is again a negative x, or negative of x to the third. The negative can come out. And so I could write that as negative x cubed, so that the cube is just applying to the x and the negative comes out. And that's because you're taking three negatives, multiplying them together, and you get a negative. Here, with an absolute value, you know that the absolute value of a negative x and the absolute value of a positive x are the same, right? Because when you take the absolute value of any number, let's say 5, or the absolute value of its opposite, you always get the same thing, right? It doesn't matter which one you plug in, because they're both the same distance from 0. So by the definition of an absolute value, because they're the same distance from 0, it's equivalent to write the absolute value of x, because the absolute value of negative x and the absolute value of x are the same. X and negative x are the same distance from 0. So that's the definition of an absolute value. That would be our definition, let's see, 3, and really definition 2 and definition 3 satisfy both of those simplifications there, or describe them. And so what I end up with here is a negative on the first term, a positive on the second term. Well, my original function has a positive and a positive. There's no way to make this equal the original function, because if I wanted to make the first term a positive, I'd have to factor out a -1. That would give me a positive x cubed, but that would then change my other sign to be a negative x squared. Okay, so I'm either going to get a negative first term and a positive second term, or a positive first term and a negative second term. I can't get them both to be the same now. Here, both signs are the same. So I know that this cannot equal, so I'll write it this way, f of negative x cannot equal the original function. Okay, I know it cannot equal the original function because the original function is both positive signs, and I can't get both of these signs to be positive at the same time. I also know that I cannot get, if both these signs are positive in the original, I cannot get both of the new signs to be negative together, okay? Which is what I would need in order to get negative f of x. And so I know that I do not have negative f of x as a simplified form either. Okay, so my original function, when I plug in the negative x, is neither equal to f of x nor its opposite, in which case we have neither even nor odd symmetry. So this must then be a neither. This has neither symmetry. Okay, so I would say f of x has neither, well, maybe not has, how about is neither even nor odd? F of x is neither even nor odd. Or you could say it has neither y-axis or origin symmetry, okay? And so there you have three examples now, one for each case, where you could have even, odd, or neither type of symmetry.